down, and as said, he called this active molecules. And nowadays, we're not saying this is active molecules, this is passive Brownian motion. And I also realized, actually, I forgot to tell you which paper of Einstein I have been talking about, and it's this one. I'll put it up here. Über die von der molekularkinetischen Theorie der Wärme geforderte Bewegung von in ruhenden Flüssigkeiten suspendierten Teilchen. That's a quite involved sentence even for a native speaker. And here's an attempt for translation on the movement of small particles suspended in a stationary liquid demanded by the molecular kinetic theory of heat. So this is the paper we have been discussing yesterday. Okay, so and the main results of this discussion were that we have been looking at a particle, micrometer in size, roughly, and this is suspended in water in an aqueous solution, and it performs Brownian motion because of the collisions, the water molecules, the impact of the collisions of the water molecules. So this is moving around, and following Einstein's reasoning, we found first that Brownian motion is basically the same as diffusion, or is a cause for diffusion, you can say. And the diffusion coefficient is given by kBT, so it's a temperature of the water, it's temperature T. Kb is Boltzmann's constant divided by gamma, and gamma is the friction coefficient of the particle. Okay? So it's a property of the particle in the aqueous solution. And we also found that D is given by the mean square displacement of the particle, which is growing linearly in time. So if we divide by D and the factor 2, here we get the diffusion coefficient. So this is a way to measure D. This is a way to connect. This is a fluctuation-dissipation relation connecting the fluctuations and the fluctuations with observable quantities here. You remember the Action Lab guy telling you if you can measure the wriggling of this particle, you learn something about the small particles kicking the big one around. Okay, and then I told you already that what we want is an equation of motion for this big particle without knowing too much about the small particles. And of course, I also said already, we could write down Newton's equation for all the particles involved, this one and all the water molecules, and then we could try to eliminate the motion of the water molecules integrating out, we can say, but this is a formidable task. One can do it only by using advanced techniques and some kind of approximations. I don't want to do that here. I want to argue on a little more phenomenological basis, but the goal will be that we instead of describing all the impacts of the water molecules explicitly by including all the water molecules, we would like to have a kind of effective description. So this force here includes, in an effective description, the forces coming from the surrounding aqueous solution, so that in general it depends on x, the particle position, and x dot, the particle velocity. So the dot is derivative with respect to time. So a is the second derivative of x, and the velocity is the first derivative of x. This is our goal. Okay? This is what we want to do in that lecture. And we already have discussed a little bit, also in the derivation of this quantity, that one of the forces acting on the particle moving through that liquid is the friction force. It's a hydrodynamic viscous friction force, which is proportional to the velocity. So the first contribution we have is a friction force here to this total force. and it's the friction coefficient times the momentary velocity of the particle. Okay, this you can imagine is like the average contribution of the water, the average effect of the water on the particle. And just out of curiosity, we estimate the order of magnitude of these forces. For a spherical particle, I also said yesterday that the friction coefficient can be calculated by solving the hydrodynamic equations, and it's given by 6 pi nu a, where u is the viscosity of the water, and a is the particle size. So in our case, like 1 micrometer, and the viscosity of water at room temperature is 1 millipascal seconds, which is 1 femtonewton divided by micrometer squared seconds. And A, as I said, is roughly 1 micrometer. It's the order of magnitude. And the velocity which the particle is moving around is also typically like 1 micrometer per second. And if you plug in the numbers here, we get a magnitude of the friction force which is in the order of 1 femtonewton. So this is a typical friction force in that system. And this we are going to compare to the other forces we will find there. So this is one contribution, like the average contribution, and then we want to model the fluctuations as well. Okay? So the second contribution here, this is the first one. The second contribution is the fluctuating force. It's often called thermal noise. Because it's a noise-like effect having its cause in the thermal energy of the water molecule. And it comes from the collisions with the water molecules, as I already said. And the thermal energy here, the energy scale involved at room temperature, 300 Kelvin, let's say, is this kBT. This is an energy scale, and if you calculate it, it's about 4 femtonewton micrometer, where kBT is the Boltzmann constant, 1.38 times 10 to minus 23 joule per Kelvin. And you see here that in the micrometer range, this energy scale is very well comparable to the energy scale you get here. So friction forces or fluctuating forces are as large as that's what you meant, right? So fluctuating forces are comparable to the friction forces. We cannot forget about these. And this is what we have seen in the Action Lab guy's movie there, when he put under the microscope like the smaller particles from the milk, that they were moving around, really like wiggling around. Okay, now how do we model this? Fluctuating force is equal to something that we usually use the letter psi for, psi of t. And this psi of t is a Gaussian white noise. It's called a Gaussian white noise. So it's, by the way, I write everything in one dimension, but generalization to higher dimension is easy. So it's called a Gaussian white noise, meaning Gaussian, meaning that its statistical properties are like a Gaussian distribution. Its statistical properties are fixed by the first and second moment. If I know the first and second moment, I know everything. And white refers to the fact that the second moment, if I look at the noise, the correlation of the noise at different time points, t and t prime, that this is a delta function. So this means that it's 0 for all values of t and 2 prime which are different from each other, and goes to infinity for equal time points. But the area under the whole delta distribution is a constant, is 1. So this is also, the consequence also is if you do a Fourier transformation, you get a constant. So if you look at the spectrum of that noise, it's constant. It's white. All frequencies contribute in the same way. Okay, that's the reason it's called white noise. And if you don't have such type of correlations, if you have, for instance, exponential correlations, people say very often you have colored noise. Here it's white noise. Okay, this is the second moment, and the first moment, what should the first moment be? It should be 0, because the fluctuating forces should not have any effect on average, right? So they don't induce a systematic motion of the particle. On average, the effect is 0. So the first moment is 0, the second moment is this. It's Gaussian, so I have fixed all the statistical properties. And then the strength of that noise here must somehow be related. I mean, this we can already guess from our physical intuition. It must somehow be related to the temperature of the water, because the temperature tells us how fast the water molecules are moving, and when they're moving faster, these fluctuations should somehow be stronger. Okay? So we put a proportionality factor here, which for historical reasons, or for many practical reasons also, is written as a square root of 2 and then times something, which for now I call gamma. Okay, we will find out what this gamma is a little bit later, but for now we expect it to somehow be related to the temperature, maybe also the diffusion of the particle, something like that. Okay, but we are going to find out what this is. Right, and this delta correlation, it's mathematically, it tells you that the noise, the impact of the water molecules, they are not at all correlated as soon as I look at different time points. Of course, in reality, it's not exactly true. The bath, the water molecules, they have a memory, but it's extremely short. So for all practical purposes, I can say that this is a delta. This is related to the assumption we had in the Einstein derivation, where he said that the successive steps of the motion of the particle are uncorrelated. That's the same assumption. So I mentioned already that this correlation time, or the collision time in water, is something like 10 to minus 13 seconds. Okay, it's extremely small. It's almost, it does not play any role for anything what we see, what the particle is doing, which is on the time scale of seconds. So about, or maybe 0.1 seconds, or maybe if we have a good microscope, milliseconds. So it's more than 10 orders of magnitude lower. So this justifies to write down a delta function here. Okay. The next thing is that we may compare the magnitude of these forces here, the inertial forces, with the friction forces. Because this is such a small object, volume effects, which is here the mass, it's proportional to the volume of the particle. This is compared to the size of the particle, they are not that dominant anymore. And if we do the calculation, if we compare the magnitude of these inertial effects, it's roughly the volume of the sphere with some density, and the second derivative. And if we now use that the particle density is roughly the density of water, which is practically the case for all the systems we consider, this would be 1 kilogram per liter, which is 10 to minus 15 kilogram per micrometer cubed. And then again, we have the particle size roughly 1 micrometer. We have, let's say, the typical acceleration is about 1 micrometer per second squared. And if we plug in all the numbers, then we get that the typical magnitude of this inertial force here is 10 to minus 6 femtonewton. So it's 6 orders of magnitude smaller than the friction force or the fluctuating forces. That means that we can basically forget about it. Okay? So inertial forces don't play any role here in these systems. If you were such a colloidal particle moving through water, it would be like, I don't know, moving to honey or even peanut butter or something that is highly viscous, that you feel as being highly viscous. So these inertial effects, they don't play any role. A more elaborate discussion of that would actually consider the time scales involved. So I already said one time scale is the one on which the water properties equilibrate. This is the collision time scale of the water molecules, 10 to minus 12, 13 seconds. The next time scale is the one on which the velocity degree of freedom of the colloidal particle relax. And this is basically m divided by gamma. This is this time scale, and then the other time scale would be the diffusive time scale of the particle, the one we are actually interested in the end, the time scale on which we do our experiments, on which we do our measurements. So they say that bath time scale is 10 to minus 13 seconds. This is around, if you plug in the numbers, it's around microseconds, roughly. And this is, say, 1.0, or if you have a good microscope, 0.1 or 0.01 seconds, something like that. So to give you an idea, so this time scale tells you if you have the particle, the colloidal particle at rest, and then you let it move, it will be kicked around, and it will take some time until it equilibrates with this surrounding solution, that it has the same mean squared velocity, the same temperature, and this time is this. So if I am the colloidal particle, I stand here, and then the water molecules start to hit me, I will wriggle around, I will move only very, very small distances. My mean free path is maybe the size of a water molecule, something like that. But I will wriggle around, I change my velocity all the time, and the distribution of the velocity is the Maxwell distribution. Okay? I equilibrate with this temperature. And the time it takes until I reach this distribution is 10 to minus 6 seconds. So if you now imagine, just to get the scale, at the fastest time scale here, the one that is related to the bath is, say, 1 second. Okay, if you imagine that would be 1 second, then this time here is about a week, if you do the calculation. And so this it would take until my velocity equilibrates with the bath. It would take 1 week. And the time you need to observe my motion until I diffusively are displaced about my own size, it would be about 10 years. So there is really a huge separation of time scales, which gives us the possibility to, in the end, write down such a model which is extremely accurate for this kind of motion. Of course, if you are interested in processes that happen on these timescales, you have to do better. You have to include maybe explicit water molecules or other things. Okay? So if we summarize these, we can put the left-hand side basically to 0, the inertial forces, and on the right-hand side we add up what we found so far, minus gamma x dot of t, the friction, plus square root 2 gamma psi of t, this noise thing, and then I can add a force F of x, which collects all other forces, which are not related to the aqueous solution. Okay, like external potentials, maybe interaction potentials, or things like that. So these are forces which have nothing to do with the solution the particle is suspended in. So my final equation I find is a first order equation in x, in the particle position. Gamma x dot equals f of x of t plus 2 gamma psi of t. And this equation is called the overdamped Langevin equation. Overdamped refers to the fact that we put the inertial effects to 0, that we consider the case of extremely high damping. As a side remark, this procedure of just equating the inertial effects with 0 is, from a mathematical perspective, a very tricky thing. Okay, because you're changing actually the order of the differential equation involved here. So the way I did it here is not the correct way to do it. You actually have to do a proper, for instance, multi-scale expansion and see what happens to your equations. Because it turns out, for the experts, if you have, for instance, a space-dependent coefficient here, that you may end up with the wrong equation by just setting this equal to 0. There is this Ito-Statonovich thing. Maybe you have heard of it. If not, it's not so important for what's going on here. Or you may ask me in the work and group sessions if you want to know more. Okay, that's our equation. That's the equation which describes Brownian motion on a trajectory level. And now we have the question, what is this gamma? Okay? What is gamma? So I rewrite this equation in the following way. Divide by gamma, by the small gamma. And typically, I very often write for f divided by gamma. This has a dimension of velocity. I write here, I use the small v symbol for that. That's the deterministic velocity, the velocity contribution coming from deterministic forces acting on the particle. So now I can formally solve this by integrating from a time 0, t0 to t1. So x of t1 is given by x of t0 plus the integral from t0 to t1 dt v of x of t plus square root 2 gamma divided by gamma squared. Here has to be a square. Integral t0 to t1 dt psi of t. Okay, this is just a formal solution, or the integral equation which is equivalent to the differential equation here. So now the gamma is a property of the heat bath only. So it has nothing to do with these other external forces F, so that I can, for finding out what gamma is, I can put it to 0. And V equals to 0 here means F equals to 0 means that it's simply free diffusion. It's an equation describing free diffusion. Okay, the particle is simply pushed around by the water molecules. And that also means that the average position at time t1 is exactly the same as the initial position, because the fluctuating forces do not have a net effect because of this condition here. Okay, that's the first moment. And the second moment we can calculate now with respect to the average. So I want to calculate this quantity here because it's related to the diffusion. And this is given by 2 gamma divided by gamma squared, and then the square of that integral. Okay, this is related to the diffusion coefficient. I already know that. And now I have to see what comes out here, so that I can relate this gamma to the diffusion coefficient. So I do this calculation here. I calculate this integral. Squared. It's the average of integral t0 t1 dt, same integral once again, dt prime times psi of t prime. Okay, I just wrote the square of the integral as 2 integrals, and now I can move the average, because it's a linear operation, into the integral. Okay, but these correlations I know. It's a delta. And the integral over a delta function, which completely contains these arguments, is simply 1. Okay, so this first integral is 1, so that I am left with an integral t0 t2 dt times 1, which is t1 minus t0. Okay, so that means that I get from this calculation that x of t1 minus x0, I use this here, squared, is equal to 2 gamma divided by gamma squared t1 minus t0. So now use t0 equals 1, t1 equals t, and then I can identify the 2 gamma over gamma squared with the diffusion coefficient. That means that gamma is basically, I can identify the 2d from over there with the 2 gamma, so that means that gamma is d divided by gamma squared. And now I have related the d times gamma squared. I have a relation for gamma to quantities which I already know. Okay, so the end result of the overdamped for the overdamped Large equation is, I can change it here, that I have 2d gamma squared. Okay, but I also know that d is kbt divided by gamma, so this is also kbt times gamma. Okay, So that tells us now that this friction, the magnitude of the fluctuating forces is related to temperature and friction here. Okay? Right. So what I want to do next is to consider what this Langevin equation tells us about a small displacement of the particle over a small time interval dt. But I think I will clean up a little bit first. So I'm considering sort of a discretized version of the Langevin equation. So the idea is to look at the motion of the particle over a small time step delta t. And small meaning here that this time step is still very large compared to the characteristic time scale of the bath, but it's very short compared to the time scales I'm observing the particles on. Okay, so this is what I mean with small. So it's something like that. The particle is doing a wild movement, and I look, maybe here is x of t, and somewhere here is x of t plus delta t. Something like that. And I can calculate x of t plus delta t from x of t. Basically, it's the same as the thing here, only that I have t0 is equal to t, and t1 is equal to t plus delta t. So this is equal to the integral t plus delta t dt prime v of x of t prime plus square root 2d integral t plus delta t dt prime psi of t prime. Okay, it's the same as before. I also used what we know about gamma now. And the thing now is, as I said, this is a very short time interval. So on that time interval, the particle is hardly moving and feeling changes of the deterministic forces, because they vary on timescales which are at least as large as the particle. So this is basically constant, this v over this integration interval, so that we can write, this is roughly the integral dt prime v of x of t, not t prime, t here. But this quantity, I cannot do the same here. This quantity is highly fluctuating. It's fluctuating a lot under the integral, even if delta t is small, because it's more related to the time scale of the bath. Okay, I cannot do anything here. I just have to keep it like it is. Like that. But yeah, okay. But then here, if this is x of t, I can take it out of the integral, and I get x of t plus v of x of t delta t And then again, this thing I don't know anything about yet. Okay, this is the result here. And this here, but I have to realize that this integral is basically integrating over Gaussian processes. So it's like a sum of Gaussian variables. It's a Gaussian process as well. So if I know the first and the second moment of this thing, I know everything. I know it's Gaussian, and I know it's 2 moments, so I'm fine. So let's calculate first and second moment. The first moment is 0, right? Because the first moment of psi is 0. So it's 0. The second moment is again such an integral like we have calculated it over there. Let's go to d, integral t plus delta t dt prime psi of t prime squared. So, and we got that this integral here, the squared integral, is simply the difference between the upper and the lower times. So in that case, it's delta t, and then we have the 2d in front. So it's 2d delta t. That means that we can, in a statistically equivalent way, write x of t plus delta t is equal to x of t plus v of x of t delta t plus square root 2d delta t and something which I call gt, and this gt is a normal random variable. It's Gaussian with average 0 and variance 1. Because I took this prefactor here, so if I have this prefactor here, I don't change the average, it's still 0, but I change the variance to this value. If the variance of g is 1, then the variance of this combined object is this, and the combined object is what we had here, so what we substituted here. Okay, and now you see this is like a discretized version. This is like an algorithm you could actually use to simulate Brownian motion on the computer. And this is called the Euler algorithm. And you can use it for numerical solution of Brownian motion as long as the amplitude of v and this here are not too different. So if this here becomes very small, if the temperature is very low or diffusion is very small, then actually your dynamics is very close to deterministic dynamics, and you know probably that the Euler algorithm is unstable for deterministic differential equations. So this here is a discretization of a stochastic differential equation. The Longchamp equation has a stochastic term, it's a stochastic differential equation, and this here is the lowest order algorithm to solve it. And it works extremely well. Somehow this noise stabilizes these solutions, so you can use it for almost anything, except this contribution is very small. Then you have to be much more careful, and you should use higher order algorithms, which there are whole books about too. An interesting thing we can see from here, that if we go back to free diffusion, where the deterministic velocity contribution is 0, and we say a displacement delta x is x of t plus delta t minus x of t, then we realize that actually delta x squared divided by delta t is equal to 2d, and this is a constant. Okay, this is related to the fact that this algorithm here has a term which is square root delta t.
What's that about? You say b is equal to 0?
Here,
The word for that.
remark. Sorry. Yeah. So this is related to the fact that we have a contribution in the discretized version which is of order delta t to 1/2, power 1/2. But if this thing here is a constant compared to the velocity, which should roughly be delta tx divided by delta t. So this is not well defined anymore. And this is the central curiosity of this Gaussian white noise, because for v equals to 0, x dot here is basically psi. X dot is equal to psi if this is not there. And we see that it's actually not well defined. So this property that it describes diffusion makes it mathematically very tricky. And you can trace it back in the end that we use a delta correlation for the noise here. If you don't do that, if you were to say, okay, I use an exponential correlation as a model, then you don't have these problems. Okay, so, but this tells you in a way that this x dot or the psi is not differentiable anywhere, but still continuous. It's a very weird thing. This is just a side remark here. And now I would like to close the circle and come back in a way to Einstein by going from the trajectory picture which we have been discussing here in form of the Lorentz equation, by going to the ensemble picture. So you remember that when we derived the diffusion equation for Brownian motion, we considered the distribution of particles rho and how it evolves. And we can do that here, of course, as well. And since the Lorentz equation describes this Brownian motion, there should be a connection between these two things. And the equation we get from the trajectory picture when switching to the ensemble picture is called Fokker-Planck equation. Here. And this is like the ensemble picture, let's say, compared to the Lorentz equation, which describes the trajectory picture of the same physical process. So I define the probability density for finding the particle in an interval x plus dx at time t. This is the rho of x and t, and I can define it by averaging delta of x minus x of t. Okay, what am I doing here? This average is an operation which averages over many realizations of the same process, and this delta function picks out a contribution every time this trajectory, x of t, of the particle at time point t hits the point x. Okay, and in that way it constructs the particle density. So here the object x and x of t are completely different mathematical objects. This here is a trajectory, x of t, and x is a point in phase space. This has to be taken with a little bit of care. In the same way, we can define a two-point probability density, where, I write down, where the particle is at x at the time point t plus delta t, when it has been, and at the same time it is at a different location in phase space y at time t. And it's given by that average. So you can write down a similar definition. It does the same thing as explained here. This is the same trajectory x of t. At time t, it hits y. At time t plus delta t, it hits x. Okay, it's a two-point probability. And then there is a very important property of this two-point distribution, which we call the Markov property, and is formalizing what Einstein used, namely that this two-point distribution can be written in that way: xt plus conditioned yt times rho of y and t. So that says that this is the probability density for x being, for the particle being at x at t plus delta t, given it was at y at t. So this is like a transition probability. And the fact that we only need to know where it was one time step before and not the whole history, not all the positions it has been visiting before, this is the Markov property. So we only need to know its starting point, if you like. Okay, just one step ahead. This is the Markov property. And this is exactly related to the fact that these consecutive displacement in Brown motion are independent of each other. This is the formal way to write it. So now I can integrate out y in that equation, and I get simply rho of x. It's the integral dy of the two-point distribution of xt plus delta t, t plus delta t, yt. So it's integral dy rho of x t plus delta t given yt times rho of yt. And this is called the Chapman Kolmogorov equation. It's a central equation in this theory of stochastic processes. And it's very much related to what we did yesterday, where we just more or less called this transition probability phi of delta x, and delta x here is y minus x. So this is the connection. This we have been writing down the same equation, basically. Okay. So now, from that Chapman-Kolmogorov equation, we want to derive actually equation of motion for rho. And we need to know what this is. This is now the transition probability from y to x over a time interval delta t. So it's like a propagator. But we know how the particle is propagating here from the larger equation. This is the equation which tells us how the particle is propagating over time interval delta t. Okay, so if we set now in that equation the starting position x of t equal to y, the final position is equal to x here in that language. And I also introduce an abbreviation for v of x of t, which is v of y, simply v, but to keep the arguments all the time. We get that x minus y minus v delta t is equal to square root 2d delta t gt. But this here, we know how it's distributed. This is the Gaussian random variable with average 0 and variance 1. So gt is distributed according to a Gaussian, which is 1 over square root 2 pi e to minus gt squared over 2, so that we find the distribution of that object very easily by plugging in. And this is actually the propagator. The distribution of this object tells us how the particle steps from y to x. So this is the distribution for the expression for the propagator. It's equal to 1 over square root 4 pi d delta t e to minus x minus y minus v delta t squared divided by 4 d delta t. Okay, and this is simply a Gaussian with a moving center, and the velocity of that center is given by the deterministic force acting at that time point, at that position on the particle. Okay, and now we plug this expression into this integral here. You see now the calculation is very similar to what we did yesterday, only that we know an expression for this propagator. Yesterday we had the phi of delta x, and we didn't know how it looked like. Now we know from the Longchamp equation. So we can do a little bit more. And for doing that, we redefine variables a little bit. Namely, we introduce x minus y divided by square root delta t. And that we write a square root here, not a delta t, is related to the fact that we know that there is a diffusive contribution in the motion, right? So that this delta x squared divided by delta t is a constant, not the delta x divided by delta t. We use this abbreviation and we plug into the Kolmogorov Chapman equation. We get rho of x t plus delta t is equal to the integral dc divided by square root 4 pi d exponent of minus c minus square root delta t v of x minus square root delta t c squared divided by 4d times rho of x minus square root delta t ct. Okay. And now, finally, the last step is exactly the same as before. Expand in powers of delta t. So we expand this exponential and this rho in powers of delta t, collect all the leading contributions. I don't work this out in detail now. You can see it would take a little while. But what you get is that rho of x t plus delta t is equal to rho of xt minus delta t d dx v of x rho of x of t plus delta t d squared dx squared rho of x and t. You see, you get two contributions in lowest order delta t, linear in delta t, one which is exactly like the diffusive contribution, and another one which now involves the deterministic forces, the v. In the limit delta t to 0, you get this on the left-hand side, divide by delta t, take the limit to 0, then this is the time derivative, and we end up with the Fokker-Planck equation. d rho dt equals to minus d dx, v rho plus d squared dx squared rho. And this is the Fokker-Planck equation. So this is an equation, and I continue here maybe. Yeah. This is an equation which is equivalent to the Langevin equation. We derived it from there, but tells you how the distribution of particles evolves over time, rather than how a single trajectory of the particle looks like. But if we calculate rho as a distribution and calculate many realizations of the Langevin equation and extract a distribution from that, we would get the same result. And here, this equation has, again, the structure of a conservation equation that the time derivative of rho is equal to minus d dx, or in higher dimensions would be minus the divergence of something which is written here, which is v times rho minus d dx rho. So that is actually the full particle flux we have here, or probability flux density in that case. And it has a part we already know, the minus d dx rho, which is the diffusive contribution. And here is a part which comes from the deterministic forces, and it's quite intuitive. It's v times rho. So the density just moves locally with the velocity given by the deterministic forces. And combining these two effects, we have to complete the full probability density flux. Is it okay if I continue for 5 more minutes? Stealing precious time from your coffee break? Okay, thank you. The final thing I want to do is, I don't think I need this anymore. I want to solve this equation in the stationary case for a confining potential. So we want to calculate the stationary solution. Which is the solution where the density, the particle density, does not change anymore over time. Okay, it's stationary. And for the case where the force, the deterministic forces, are deriving from a potential. So I'm okay, let's stick to one dimension, like that, u of x. Okay, and the potential is confining, so it's something like that, a parabola maybe, if you like. You can think of a harmonic potential. So if this here, d rho dt, is equal to 0, the j here, the divergence of j is also 0. So that means that j has to be a constant. but J characterizes the flux of the particle. So if the potential is confining like that and you're in the stationary case, nothing can move anymore. The particles cannot move on average. So it means that this constant here is 0. Okay? So for that case, we have that this part here is 0. So the V times rho minus d rho dx is equal to 0. And the V here is the f of x divided by gamma, which is minus 1 over gamma du dx. Okay? But this here is a differential equation in one dimension, linear, so we can easily solve it. And the solution is e to minus u of x divided by gamma d. So the gamma from here and the d from here. And then we need a normalization condition, because this is a probability density which has to be normalized. So now the thing is that this situation, a stationary probability distribution of particles in a confining potential, corresponds to an equilibrium situation. The particle has equilibrated with the surrounding bath. And for an equilibrium situation, we know what the distribution is. It's the Boltzmann distribution. So this thing here must be the same as the Boltzmann distribution, which is e to minus u of x divided by kbt. So from that we see again that d is equal to kbt divided by gamma. And here we found this equivalence from using equilibrium statistical mechanics, from using what we know from statistical mechanics, like we did it in a different way yesterday. So we again find this fluctuation dissipation relation by comparing an equilibrium solution of this dynamical process to what we know from equilibrium statistical mechanics. So all this, what I described here, is a dynamical approach to describing the motion of these particles. And as such, because it's a dynamical approach, it goes beyond equilibrium situation. It covers non-equilibrium as well. So this is a natural way to describe non-equilibrium phenomena in these systems, because you can have driving forces like this V here. You can make them even time dependent. You can consider also temperature gradients. You can consider concentration gradients of mixtures of particles, all in the same way. So you can consider various non-equilibrium situations and then use these tools here to try to understand them. This is a quite generic approach right now, using the Langevin equation for these kind of systems. If you don't want to know about processes that go on really fast time scales, where, I don't know, proteins change conformations or things like that. The things that, for instance, Fernando has been talking about, also Eduardo, and so on and so forth. And I also tried to make clear that the structure of the equation, or much of the structure of the equation, relies on this huge separation of timescales. So whenever you have such a situation also in other systems, you can use similar tools. You can use the tools of stochastic processes. And this is another reason why they are so important, that they find application also in chemical reaction kinetics or economy and many other areas. Yes?
Could you explain
Yes. Yes. So in equilibrium you can define as the absence of macroscopic currents. So if you observe the systems, all the observables you have don't change over time. In particular, there are no currents. A steady state can have a current. You can have cases where the distribution here does not change over time, but the J is still not equal to 0. In particular, higher dimensions. Imagine a two-dimensional system. For instance, you can have the following system. Imagine a two-dimensional parabolic potential, which is not perfectly round, but ellipsoid. This is in 2 dimensions. Okay? Can you imagine what I'm talking about? The potential comes out here. These are equal potential lines. And then you apply, for instance, you can do it like that. You connect the particle in that way to 2 different heat bars. This may be a cold temperature, let's say, and this may be a hot temperature. And since this is still a confining potential, the distribution that will develop here will have this property. It will not change over time. It will be stationary. But if you look, you can solve it explicitly, this thing. If you look at J, you will actually find that there is, on average, there is a rotating current in that system. So the particle is moving in circles on average. So this is a non-equilibrium system with a steady state. And there are many more examples. This here is called the Brownian Generator. It's a fun system because you can calculate it, you can solve it explicitly. You can write down the full solution. Does that answer your question? Okay. Yeah, I'm also at the end of my lecture, so if there are more questions, please go ahead. You can also go for coffee and come back later with questions, also fine. Okay, let's go for coffee.
How should I use this? Do you need help? Yes.